Hey guys, welcome to Skill-Lync. You might have definitely played using magnets in your childhood days. Do you know why only a few materials are attracted by magnets? If not, that is what this video is about. In this video, we'll be discussing what magnetism is, the different phenomena of magnetism, domain theory, hysteresis, and the types of magnetic materials. So let's get started. Almost all materials are affected by magnetic field up to a certain degree. So it becomes necessary to study the magnetic properties of the material. The property by which the materials are attracted or repelled by other materials is known as magnetism. The principle of magnetism and magnetic materials are used in so many devices like electric motors, generators, transformers, radios, televisions, etc. Let's get some basic ideas before moving into the topic. Like a battery which has a positive and negative terminal, a magnet has a north and south pole. This is said to be a magnetic dipole. The force exerted by the material due to the presence of magnet is known as magnetic force, and the area within which the magnetic force exists is known as magnetic field. As we know, a current carrying wire acts as a magnet. In a similar way, the electron, being an electric charge, exerts a magnetic dipole moment. The magnetic moment is due to two different kinds of electron motion. The electron rotates around the nucleus in the orbit. Also, it spins on its own axis. The orbital rotation and spin of the electron may either be in clockwise or anti-clockwise direction. The total magnetic moment exerted by the particle will be the sum of the individual orbital and spin moments of the electrons. You might have learned about electronic configuration in your earlier classes. If you are aware, you know that the atoms can be either completely filled with electrons or partially filled. In completely filled atoms, each electron has a pair that rotates in the direction opposite to its pair. This in turn nullifies the magnetic moment because of their opposite sign. If the atoms are not completely filled, there will be unpaired electrons which contribute to the magnetic moment. Thus, the electronic configuration of the atom plays a vital role in determining the magnetic property of the materials. Moving on, the magnetism exerted by the materials can be divided into three types. They are diamagnetism, paramagnetism, and ferromagnetism. Assume we have an atom with completely filled electrons, that is, all the electrons are paired. Here, the magnetic dipole will be absent at normal conditions. But when a magnetic field is applied to it, the direction of orbital rotation changes, which in turn orient electrons in the opposite direction, repelling the magnetic field. This type of magnetism is known as diamagnetism. This is weak in strength and it persists only up to the application of the magnetic field. For instance, if the atom has unpaired electrons, then they develop permanent magnetic dipoles. However, the strength of the field due to these magnetic dipoles will be infinitely small. But as soon as a magnetic field is applied, the magnetic dipoles orient themselves in the direction of the magnetic field, and now the strength of the field will be comparatively high. However, the magnetic property gets lost when the applied field is removed. This type of magnetism is known as paramagnetism. But there is an exception to this case. Some materials with permanent magnetic dipoles can have a strong magnetic field that can exist even after the removal of the applied magnetic field. This phenomenon is known as ferromagnetism, and the materials that exhibit the property are known as ferromagnetic materials. Iron, cobalt, and nickel are of this type. The areas in which the magnetic dipoles mutually align themselves within the ferromagnetic material are known as domains. Each domain is separated from each other by domain boundary. When a magnetic field is applied to ferromagnetic material, the dipoles in all the domains align together in the direction of the applied field, and the same condition persists even if the field is removed. The maximum attainable magnetization in ferromagnetic material is known as saturation magnetization. This value decreases with an increase in temperature due to the intermolecular vibrations. The saturation magnetization drops gradually and becomes abruptly zero. The temperature at which this happens is known as Curie temperature. As said, an applied magnetic field induces magnetism in the material. The strength of the magnetic field is expressed as field strength, denoted by H, and the induced magnetism in the material is expressed as flux density, denoted by B. Let's point these values in a graph. As the field strength increases, the flux density increases until it reaches the saturation point. Similarly, when the field strength is reduced, the flux density reduces, which will not follow the same path. This ends in the reverse saturation point. The effect by which the developed flux density lags behind the applied field strength is known as hysteresis. Based on the hysteresis, ferromagnetic materials can be divided into two types. If the shape of the hysteresis curve is small, then the material can be easily demagnetized. This type of material is said to be a soft magnetic material. It is used in devices which are subjected to alternating magnetic fields. On the other hand, if the hysteresis is large, then the material is said to be a hard magnetic material. That is, this material cannot be demagnetized easily, so it is used in permanent magnets. So that is all that we're going to discuss in this video. We'll meet up again in the next one. Until then, bye.